In commercial application, designing new elements for aperture-shared array is time-consuming. For quick deployment, the mature low-band and high-band elements operating at 690 to 960 MHz and 3400 to 3800 MHz respectively, are usually used to design the dual-band aperture-shared array. However, the high-band radiation is generally blocked and distorted by the higher low-band element. As a result, a systematic approach to reduce the blockage effect without changing the antenna performances is indeed demanded. To reduce the blockage effect and maintain the antenna performances, the current distribution on the planar monopole is analyzed. As seen, the H-field in the middle is opposite to each other, and cancelled out. Thus, the middle parts of the element arms can be hollowed to form the slot unit cells, and high-band pattern is improved without changing the low-band performances. For demonstration, the simulated results are shown and validate the conclusion. The low-band element with slot unit cells operates at mode 1 and mode 2. When the low-band element is illuminated by the incident wave, it works at mode 1. In contrast, the low-band element operates at mode 2 as the feed source excites itself. Based on the analysis of slot unit cell, the equivalent inductor and low-pass circuit are obtained in mode 1 and 2, respectively. To reduce the blockage effect and maintain the low-band performances, the prototype circuit is proposed. In mode 1, a capacitor is loaded to form a first-order filtering circuit and pass the high-band signal. Meanwhile, the impedance of the series capacitors in mode 2 is large at low band. Thus, they become an open circuit and rarely affect the low band performances. To realize the prototype circuit, a patch is loaded to the slot. Due to the wide width, its self-inductance can be ignored, and thus the first-order filtering circuit and series capacitors are obtained in mode 1 and 2, respectively. The unit cell model consisting of slot and patch is simulated, and the circuital parameter Y is solved. Since the parameter Y comply with the characteristic of parallel resonance, the first-order filtering circuit is validated. Moreover, seen from the simulation result, a first-order filtering response is realized. Within 3200 to 4200 MHz, the reflection coefficient is less than -10 dB, indicating that a wideband and good transmittivity performance is obtained at this band. The low-band element loaded with unit cell is simulated. The results are shown in this slide. As seen from the comparison with and without the unit cell, the high-band pattern is significantly improved, and the performances of low-band antenna are maintained same. A dual-band aperture-shared array antenna is fabricated and measured. The measurement results are consistent with the simulation results. Moreover, the gain, 3 dB beam width and reflection coefficient comply with the requirement of base station antenna, as described in the paper.
Hi, everyone. I'm excited to share our research on highly selective Filtennas with wide-stopband based on multifunctional slots-loaded substrate-integrated cavity. Frequency selectivity is a key indicator of Filtennas and has gained significant attention. A common way to achieve high selectivity is by creating radiation nulls near the passband. 3 typical methods to construct radiation nulls. First, using multi-layered structures. Second, coupling parasitic elements. Third, introducing slots or pins. However, these methods often face challenges such as large size, high profile, and complexity. In our work, we propose a new method for designing highly selective Filtennas. We introduce the half-mode patch, which is more compact and has fewer harmonics for mode excitation, making it suitable for wide-stopband antennas. Next, we introduce the first work. It builds on antenna 1, creating antenna 2 by coupling a parasitic patch, and then forms antenna 3 using SiC packaging. Antenna 3 has an H-shaped slot loaded in the SiC. The performance comparison shows that antenna 3 has a wider bandwidth and more radiation nulls. Both half-mode patches can radiate, with one resonance at 3 GHz and the other at 3.17 GHz. RN1 is regulated by the gap position. RN2 is controlled by the slot insertion depth. RN3 comes from weak radiation in the feeding line and can be adjusted by changing its length. Now, we demonstrate the performance of work 1. It has notable advantages like a wide stop band, multiple radiation nulls, high efficiency, and stable gain. Building on work 1, we propose work 2. By dividing the H-shaped slot into two opposing C-shaped slots, a half-wavelength resonator is formed. This creates a CT coupling diagram with two patch resonators, introducing a radiation null in the lower stop band. The comparison shows that work 2 has a wider bandwidth and higher selectivity. Work 2 still relies on two half-mode patches for radiation, while the half-wavelength resonator provides in-band resonance. RN4 can be adjusted by changing the width of the resonator, and the bandwidth can be modified by changing its position. Next, we demonstrate the performance of work 2, which shows a wide stop band and higher frequency selectivity. In conclusion, we have listed several key indicators for the two works. The Filtennas proposed offer the following advantages: lower profile, more compact size, higher frequency selectivity, simpler structure, and improved stop band rejection. Thank you for your attention, and we welcome any questions you may have.
It's an honor to present our research on wideband millimeter wave filtering magnetoelectric dipole antenna with high out-of-band suppression. Millimeter wave has received attention due to its advantages. In millimeter wave RF systems, filters are usually needed to suppress the noise. Traditionally, antennas and filters work separately, resulting high insertion loss. Filtering antennas, which combine filtering and radiating functions into single structure, become important. The filtering method is explained step by step. ANT1 is a directly fed ME dipole with a meandered strip line, which generates null 1 at 19 GHz. ANT2 is evolved from ANT1 by introducing two split rings, which generates null 2 at 18 GHz. ANT3 is realized by adding two straight strips, which generates null 3 at 39 GHz. ANT4 is completed by replacing the direct feeding line of ANT3 with a pie-shaped coupled feeding probe generating null 4 at 35.8 GHz. At 19 GHz, the meandered strip line is short-circuited at point A. RF signal cannot pass through the feeding probe and null 1 is generated. At 26 GHz, ANT1 can be excited normally. At 18 GHz, the direction of coupling current on the split rings is opposite to that of current on the E dipole. The radiation cancels out. Therefore, null 2 is generated and the out-of-band suppression for E dipole is achieved. At 26 GHz, the current has the same flowing directions, and their radiation will be superposed. The out-of-band radiation of M dipole is suppressed at 39 GHz. The lower current loop is clockwise and equivalent to magnetic current M1. The upper current loop is counterclockwise and equivalent to magnetic current M2. M1 and M2 are roughly equal in amplitude but undergoes 180-degree phase reversal. Radiation of M1 and M2 cancels each other, thus generating null 3. At 26 GHz, current on the strips is very weak. Only a current loop is formed and ANT3 radiates normally. The stop band suppression is further enhanced by introducing the pie-shaped feeding probe. At 35.8 GHz, a current 0 point is generated at point B, and the energy cannot be coupled to the E dipole. Therefore, null 4 is generated. Differently, strong power is coupled to the E dipole at 26 GHz. The impedance matching is also improved by capacitive coupling. Finally, a pair of gamma-shaped probes are arranged. Most of E-field power is limited, and the efficiency of the proposed antenna in the higher stop band is lower by 6.7 decibels. A 1x4 antenna array is designed. The fabricated prototype and test environment are shown. The simulated results of the proposed element are presented, which has good performance. The measured results of the proposed array agree well with the simulated one. The proposed array also features great advantages. Thank you for watching.